Hess's Law is a lot of fun. It's just a really useful thing, and it's fun to do. So let's see if we can't see about both of those things. Why is it useful? Many equations take several steps to happen, and sometimes we know the heat of different processes, but we don't know the heat of the thing we care about. So what we can do is we can add equations together. So we're going to add equations, and if we add the equations together, we add the reactants on one side, add all the products on the other. If we then add the delta H's, we will get the delta H for the target equation. So let's do an example. It'll make more sense after we do one. Let's say we have C2H6, which is ethane, plus 7/2 of oxygen, and we want to find out how much energy we would get out if we made 2 carbon dioxides plus 3 waters. And in this case, we're going to talk about liquid water, so we better label everybody else as well, because they're all gases. So there we go. And the delta H for this, let's just say we don't know. But we want to know. We just don't know. We don't have any data for it. So let's find some equations that we do have data for. We're going to put this in a box, and I think this is a good practice to do because this is our target, okay? We're going to write a lot of equations on this page, and it's nice if we kind of box off the target so that we make sure we know what we're heading for and we don't get it all messed up in the jumble of equations we're going to have written down in a little bit. So here's some equations we do know the heat for, and we're going to see if we can use them to get to the heat we want. So we're going to say if we make carbon dioxide out of its elements, see, we've got carbon and we've got oxygen, we're going to make carbon dioxide. We happen to know the heat of that. We know that the delta H for this is negative 491.9 kilojoules. Okay, point. Get that point in there, Cheryl. Okay, good. Now, we also know another one. We know that H2O, this is liquid, if we break down H2O liquid into hydrogen gas and oxygen gas, we only get a half of a mole of that because we don't have as many in our original water molecule. That delta H for that is going to cost us, so it's a positive 357.2 kilojoules. And we also know that if we take C2H6, which is our ethane, and we make it into its elements, 2 carbon solid plus 3 hydrogen gas, that we are going to have to pay 105.9 kilojoules. That's also endothermic. We have to put heat into it. Into. Okay, so here we are. We've got 3 different pieces. All of the pieces in our target equation appear somewhere in these 1, 2, 3 equations. I might even number them just so we know what we're talking about. But they don't necessarily appear where we want or with the right coefficients or anything. So if we just flat out add these 3 equations, we are not going to get our target. So that's not a very good thing. So we're going to have to do some manipulating to make sure that we get what we want. So I kind of like the look of equation 3, don't you? Look at that. On the left we have ethane, and in our target equation on the left we have ethane. So let's just write that down here. C2H6 is 2 carbons plus 3 hydrogens, and the delta H for that is 105.9. Now you notice I'm just copying over something I already had, but we'll get to something different in a minute. What about carbon dioxide? I'm going to leave oxygen for now. It's the next thing in our target equation, but if you look down at your other your pieces, oxygen appears twice. O2. We've got O2 in equation 1, and we've got O2 in equation 2. So I don't want to deal with him yet because he's going to be complicated. It's better to deal with the things that only appear once in our equations that we're going to add up. and it'll be much clearer what to do with them. So this is number 3. We're just going to copy it. But this is number 1. We're going to change him. Number 1 has carbon dioxide. Carbon dioxide doesn't appear in either of the other 2 equations, so we know that whatever carbon dioxide we get for our target has to come from equation 1. So let's look at this and say, oh, in equation 1 we have only 1 carbon dioxide, but in our target we need 2. So I'm just going to multiply that whole equation by 2. I'm going to say 2 carbon solids plus 2 oxygen gas molecules will make 2 carbon dioxide gas molecules. And since I'm making twice as much of it, I'm going to get out twice as much energy. So I have to double the negative 491.9 kilojoules. I'm going to have to multiply that by a big 2. So that I show that I have doubled the equation. Okay, so we figured out what to do with equation 3. We figured out, just not changed it at all. We figured out what to do with equation 1, multiply it by 2. What about equation 2? Now, the key thing in here that I see is that it's got water in it. And water appears in our target equation. Water only appears once in our little 3 equations here. And it only appears once in the target, so we have to make it match. So I'm going to take the water in equation 2 and say, look, I have only 1 here, but I have 3 in my target. So I'm going to have to multiply this equation by 3. But if all I do is multiply it by 3, I'm going to have water on the wrong side. It's not going to match the target equation. So since water is on the left in this number 2, and it's on the right in the target equation, not only am I going to have to multiply by 3 to make the coefficients match, I'm going to have to flip-flop the whole equation. So that's what I'm going to do. I'm going to take the products, which were hydrogen gas, right? But I need to multiply it by 3. I'm going to take oxygen gas, which was 1/2, right? But I'm going to multiply that by 3. And then I'm going to flip-flop the reactant over to the product side, and again, I'm going to multiply it by 3 water, liquid state. And now, for the delta H for this guy. Remember when we flip-flop equations, if it costs us energy to break up the water, we're going to gain energy if we make the water back. And so what used to be endothermic is now exothermic. Not only that, but we're doing 3 times as many molecules. So we're going to have to take a -3 because we flip-flopped it. Anytime you flip-flop it, if it was negative, it becomes positive. If it was positive, it becomes negative. So we're going to take a -3 times our 357.2 kilojoules, and that is the energy for our new equation 2. So I think I've done everything that I need to do. Notice I didn't even mess with the oxygen. I didn't mess with the carbon. I just went after the things that were in the target equation. Sometimes with these little guys you have to mess with some of the intermediate products that don't show up in the target. But in this case I think we're going to be okay. So let's see what we have. We have on the left, when we add equations in algebra, the thing we can do is we can eliminate things that appear on both sides, right? So let's see if we can't do that here. On the left side in equation 1, now notice the numbers, I have 2 carbons. I have 2 carbons on the right side in equation 3, so I can cancel them out. I probably should have been good and put in my little states here, because it is important to make sure that you cancel out a solid with a solid. Carbon that's been turned into a gas is quite different than carbon that's a solid. So let's just make sure we've got the same thing. The other thing that doesn't appear in my target equation that I really probably am going to need to get rid of is hydrogen gas. Notice in the target equation there's no hydrogen gas. But in equation 2 I have 3 hydrogen gas molecules. In equation 3 I have 3 hydrogen gas molecules. So that's the left and the right of the arrows. The arrows is like our equal sign. So we can just eliminate them. So I think now we're going to be good. So let's add up our equations. On the left side, I have C2H6, gas, and here we go with oxygen, which I said was going to be complicated, but it's not too bad. 3 times 1/2 is 3 halves. Plus 2, hey, that's 4 more halves, so we have 7 halves altogether. 2 and 3 halves, 2 and 3 halves makes up 7 halves. Okay, so that's good. And then we can go over to the other side. I have 2 carbon dioxides, and I have 3 liquid waters. Hey, that added up to exactly the same as my target. It matches the target. That is good. If it doesn't match the target, we're in bad shape. So, matches target. Yay. So we're good. So now, we have already fixed all of our delta H's, and we've done what we need to do to them. So now we're going to take 105.9, we're going to add it to 2 times negative 491.9, and we're going to add it to negative 3 times 357.2, and when we do all of that, our new delta H is negative 1949.5 kilojoules. And so we are predicting that if you would burn some ethane in oxygen and form carbon dioxide and water, it ought to produce a negative 1949.5 kilojoules of energy. So that is Hess's law. We are basically taking some component reactions that we know the delta H is for, and we're using them to add up to our target equation that we don't know the delta H for and we want to find. And this is very useful when you have equations that you don't know the heat for, and some things, this wouldn't be bad. You could do this in a calorimeter and you could measure it, but some things are pretty hard to do in a calorimeter, or you can't, it's just not going to work out because of reaction conditions or whatnot. So in this case, in that case, it's a kind of an essential way to find out the delta H.